Welcome to today's anniversary webinar with your second desired topic: how does your PCB layout influence the costs in PCB manufacturing? I am Andreas Schilb, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker of today's webinar is our expert Jürgen Wolf, Head of Advanced Solution Center at Würth Elektronik Circuit Board Technology. Welcome, Jürgen. And now I wish you lots of fun and new information.
So a warm welcome from my side as well. And I hope that you will enjoy the next hour for our topic: how does your PCB layout influence the cost in PCB manufacturing? So let's have a look on what I will show you today. So we will have different topics like PCB size and assembly arrays. We will have a look on the copper price development and the choice of materials, as well as what do we do with the materials within the PCB stackup. Then we will go on to the mechanical processing of the PCB and what your influence is in the cost for mechanical processing, move on to enhanced technologies, and in the end, I have some more tips and tricks for you how you can avoid cost in your PCB. So let's directly dive in. One of the major points of cost in the PCB basically is the size of the PCB. The smaller the PCB, well, the higher the number of PCBs we can fit onto our production panel. And since a lot of cost during manufacturing is related to parallel processing and costs which are divided for one panel, the more PCBs you get onto one manufacturing panel, well, basically the less cost you get for one PCB. So the smaller it is, the better it will be from cost size. And yeah, we know that sometimes from component point of view, everything is already occupied on the PCB. Then maybe changing a package of some or other component could be beneficial. This depends on your application, but the main thing is the more PCBs we can fit on one production panel, the more we can split the cost for this production panel onto these PCBs. Another thing is the error proneness and the yield. So imagine we have a PCB which fits only 2 times onto our manufacturing panel. And there is only one mistake on this panel. So we are not flawless. We make mistakes as well. So our yield is not 100%. But if we have only 2 PCBs, it means one is defect. Well, then we have a yield of only 50%. Imagine we have 100 PCBs on a manufacturing panel or on a production panel. Well, if there is one defect on this panel, it's still 99 good PCBs, and we have a yield of 99%. So you see, this is, again, one thing that may help you if the PCB is just too big. We have to think about how many PCBs do we put into production so that we have an overhead to still serve your desired delivery quantity. And we have to do more of that, the bigger the PCBs are. And one last point, and I just added that recently, is the sustainability. Well, that's quite clear. The less material we use in manufacturing, the smaller the footprint of the PCB is, and therefore the better for you and the environment, basically. But PCB size is not everything. It's another question of, well, how many PCBs can we put onto the manufacturing panel? And therefore you need to know how big are these panels which we are using. And there is some background information here for you. I won't go into every detail, but basically FR4 materials or PCB materials are being manufactured in large panels. And basically all these manufacturers have a standard format. And these standard formats are being cut into different pieces so that the PCB manufacturer itself can work with it. And here you see the pieces what we are using in our fabs. So the prototype fab is using the US format divided by 8. So this would be 460 by 305. Then we have the quarter US format, which is our standard format in our plants in Niedernhall and in Schopfheim. And then we have the jumbo format, which is a quarter of the uni format. So you see there are different possibilities here, and almost all the PCB manufacturers are using one or the other format, since this comes from the cutting of these general panels which are used when the manufacturers of the materials are preparing their material. So what else do you need to know? Well, we are not using, when we say we use a quarter US format, the standard format, then we cannot use the complete 100% area. There is still a frame or a border for registration and labeling. So this is space which cannot be used for your PCBs in the manufacturing. So this has to be subtracted from the actual manufacturing panel. And now again, imagine you have 3 PCBs, and these 3 PCBs, their final contour is being routed. And this is an example here. So they would basically fit inside of this area. And if you just change the way how the PCB is going to be singularized and finalized from routing to V-scoring, then maybe we could fit 1 PCB more into this active area. And in this example, that would mean you have 33 more circuit boards on a production panel. So the price for 1 production panel basically is being divided by 4 instead by 3. And so the cost is going down. And this effect, this is greater the smaller the PCB gets. So when you look on routing, the distance between the PCBs always needs to be the same. This is due to the routing tools and the stability of the manufacturing panel. But for V-scoring, well, basically this distance is just much less, and therefore the smaller it gets, the more PCBs you get onto a production panel when you use V-scoring. Here in this case, the difference is really huge if you compare 85 PCBs or 85 compared to 56. So it's quite a huge key you can use to lower the cost here by just changing the way how your PCB is going to be simulated. In the morning, we had the webinar for our German-speaking customers, and there was one remark regarding this. V-scoring, basically, if you do not know what it is, well, you make a cut from top and from bottom into the PCB, which looks like a V, and you can break out the PCB afterwards. Breaking out means that you have to have a closer look onto your components, especially if you have ceramic components. You need to have a look how far away would they be from the breaking area. So this is one drawback you have to look at, because V-scoring is still some kind of breaking of material to singularize the PCBs. But if you have the information, you can have a look in it if it works. And another thing you have to look at, V-scoring only works if you have straight lines. So if you have rectangular PCBs, that's okay. If you need specific routings, like specific corners or whatever, then maybe a combination of V-scoring and routing would be helpful as well. Or unfortunately, V-scoring would not work and you have to go to routing. But yeah, for you to keep in mind, if you have rectangular PCBs and if you can use, for example, breaking, then V-scoring could be an option for you to get more PCBs onto our production panel and to lower the cost. Another example is if you have PCBs in an assembly array. Here in that case, the assembly array is so big that we just can fit one of these assembly arrays onto our manufacturing panel. And by just decreasing it a little bit, make it a little bit smaller, maybe we could go to the part that we can fit, in that case, 2 of these delivery panels or assembly arrays. So the cost could be almost half of the one of the left side when we do the routing compared to the V-scoring. This is not an absolute cost reduction. It's always a little bit to deal with. How big is the PCB? How big is the assembly panel? So here again, the suggestion would be get in contact with us. we would like to try to find the best trade-off, I would say, for you and for us, what fits best into our production. But yeah, we know you need to take care about your production as well. If you do assembly, your assembly machines must handle those assembly panels as well. Therefore, it would be best to get in contact and we see what would be best for us and for you as a size for this arrays. So let's see what could happen if we go in a real calculation. So we take a 6-layer board with a base material TG150. In that case, PCB size would be 20 by 40 millimeters squared. The array size for assembly would be 210 by 140 square millimeters. We have 100 micron track line and space, 500 drills. The smallest drill bit diameter would be 0.2 millimeter. And we have nickel gold as a solder surface. So let's see what happens. This would be the arrangement when we do V-scoring overall for this assembly array. And I won't go into much details here. You can later have a look into the presentation and maybe into the movie again. But you see, if we take the V-scored calculation as 100%, you see the increase by just distancing the PCBs to each other. The more distance you have, the less PCBs we get onto the array and onto the manufacturing panel. And therefore, it's still the same size of PCB, but you can increase the price by using routing just by quite a big margin. To give you a hint what you can do, we have this table here. You see our different formats. You see in which plant we produce them, which technologies are being used for that. And you see our panel sizes. And most important for you, you see the usable area. So this is the area which we can occupy with your PCBs. And then you can try and play a little bit by yourself. You can see, okay, how many pieces or how many arrays could be fit into this area, so that you can try and to max the PCBs onto our manufacturing panel. On the bottom of this table, you see basically an assumptions. If you know how many arrays you will need or what the array size would be, you can assume when you do the V-scoring, how big would be the optimal arrays to get the maximum out of our production panel. There are some tips behind. So we know that you need an edge of the array for handling, for example, during assembly. That's mostly a minimum of 5 millimeters. A lot of customers are doing 8 to 10, especially when it comes to routed outlines. If you have two edges with V-scored outlines, it could be 5 to 10 millimeter. And one big thing you have to think of is the size of the array should always be based on the thickness of the PCB, because well, the thinner the PCB or the thinner the array is, the more unstable it gets during your handling, for example, in the assembly line. If you compare an 0.8 millimeter thick assembly array with a 1.6 millimeter thick, the 1.6 millimeter is quite stable. 0.8 already tends to bow. Depending on how the handling is in the assembly. So maybe you need to have a specific assembly system, or you need to put something underneath the PCB to stabilize it. It depends on your assembly line, but so yeah, please take in mind, the thinner the PCB is, the more flexible it will get, and it will maybe start to bend when you try to occupy it and try to handle in your assembly line. So it's again a trade-off of stability and cost. Let's move on to copper. And I've shown this slide quite often. And the last webinar about this topic was 2020. So you see 2020, we were somewhere in the range of 6,000 here in this chart. And we already had quite a rise at the end of 2016 of almost 50% in copper price. This was due to basically the start of the mass manufacturing of all these electric vehicles. Copper foils are being used in high amounts in batteries for electric cars. So all the copper foil manufacturers decided to say, okay, we prefer another market, not the PCB market. And if you want to have PCB graded copper foils, well, then you have to pay more even that. So the price went up. And you see in this chart during 2020, well, the price went up again. So that when you compare 2016 to today, the price for copper on the stock market, well, basically almost doubled. So if you use copper on a PCB, we have to pay the copper price. Therefore, you need to think about how much copper do I need. That's why I added this chart and I upgraded it from last time. So the base here basically is always the 35 micron copper clad laminate. So for each chart, this is the 100% price. And if you just compare it, the more copper you have, so the dielectric is the same. When you look on the first part, 0.51 millimeter with 18 micron copper, 35 micron copper, 70 and 105, you see how the price goes up just by using more copper. Yeah, for sure, because the copper is expensive. But what else do you see? The comparison between 2020 and today. So the blue lines is again based 100% on the 0.51 or on the 35 micron price from 2020. You see that, well, especially for the high copper, we almost have 3.5 as a factor times 3.5 compared to 35 micron and compared to July 2020. So prices are going up, and it doesn't matter for which material. It's always the more copper you use, the more you have to pay. So the question is, what is necessary or what is possible? Yeah, I know if you have like a current carrying capacity which you need to fit into, the question is, do you need, for example, 70 micron copper and have thinner track widths, or would you use 35 micron, and if you have the space on the board in the layout, just make them wider? Because at the end of the day, for current carrying capacity, it's the cross section of the track, not only the thickness, it's the cross section. So maybe you find a trade-off if you have the space to use 35 micron and make the tracks wider, and you have still the same current carrying capacity. Maybe even a better heat management due to the more area you're using with the copper, and the heat can spread more into the area. So it's always a question, what is necessary or not? What do I use? Because yeah, the more copper you have on the PCB, when we do the etching, the more copper we have to basically throw away after the etching, because especially for inner layers, this is still a subtractive process. And the less we have to throw away, the better it is. And therefore, yeah, use as much copper as you need and think if maybe 105, 70 or 35 is enough for your application. We have a lot of customers who came from the past, which always had in their specific requirements, even if they wouldn't need it, 35 micron on the inner layer. That was basically a standard. But if you see this and compare it, 35 micron to 18 micron, you still can get down in price. So if you only have signal layers on the inner layer, or you have big crown planes or whatever, ask yourself the question, do I need the 35 microns on the inner layers, or would 18 microns, for example, be enough? So this could already be quite a factor to get down in pricing. Then we will have a look on the different solder surfaces. This is not a chart of every solder surface out there on the market. For example, there is no organic solder protection, OSP, in here. There is no EPIC, there is no whatever. But it's the most common surfaces which we have in our plants. So it's hot air leveling lead-free, chemical tin, chemical silver, nickel gold, and plated gold. And I wrote down here the thicknesses of the materials. And my colleague was so funny to add this rocket, just to give you the impression, when it comes to plated gold, it's really the question, how much gold do you need? Because the thicker the gold, the more you have to pay. And we actually calculate gold on a daily basis. So it depends on what is gold, the cost for gold on a daily basis. And to show you this, on the next slide, I have basically the gold price. So electroplated gold is often being used for example, on contacts due to abrasion. If you want to plug in and do not destroy the contact, a lot of times a thicker gold is often being used for that. And you still want to do soldering, so it's often even a combination with nickel gold, because when you do the soldering, you do not want to have too much gold. Too much gold would make your solder joint very brittle. So it's often a combination, and so you have already two solder surfaces. And there are even some applications which go up with the gold thickness up to 4 microns compared to the standard gold thickness with nickel gold, which is somewhere of between 50, 70, 75 micron of gold. Well, this is quite a lot. And so when you look on the chart, this is really a price which changes quite a lot. You know, the gold price is changing quite a lot depending on global events. And in the last webinar, we already had a very high level for the gold price, and this level is still going on up until today. But it still can change 10%, 50% on some weeks. So it's really interesting to see how much gold do you actually need to get the price down. So do you really need 4 micron, or would 2 microns be okay as well, for example? Next thing we would like to talk about with you is the PCB stackup. And here for you, some examples. The first example is a comparison of a 4-layer multilayer with different thicknesses. So the industry standard is basically 1.55 or 1.6 millimeter. And you would find a suggestion of a stackup on our website, and we would call it ML4, which means multilayer with 4 layers. TG150 would be the material grade, 1.6 millimeter thick, and a 35 here would mean that the inner layers have 35 microns of copper. So how is the construction here? We would use an 0.71 millimeter thick FR4, which has 35 microns of copper cladding on top and on bottom for the inner layers. And then we have 4 prepregs, 2 above and below of this inner layer core, 2 copper foils, and so we would press together this 1.6 millimeter PCB or production panel. If you want to have it 3.2 millimeter thick, it's still a 4-layer multilayer. To do this, we would exchange the inner layer core. We would just make it thicker to 2.4 millimeter, for example, to get up to the 3.2 millimeter. And if you want to have it thinner, we would change the inner layer core down to 0.41 millimeter. And we would change the prepregs from the glass cloth type 7628 down to 2116, for example. We can make it even more thin or much thinner, 0.5 millimeter. Well, here we would have to use a 100 micron core, and we would have to use 1080 prepregs. So what is the difference here overall? So we change the thickness of the dielectric of the core which we are using, and we are changing the prepreg styles. The thinner the glass gets, the harder it is to handle for the manufacturer of the FR4 material. So a 1080 prepreg or a 106 prepreg, well, they have to run their processes just slower because the risk of breaking the glass cloth during the impregnation is just higher. So that's the reason why when you compare the cost and you say 1.6 millimeter, the standard would be 100%, you can go down in cost when you still use 0.4 millimeter or 1 millimeter thick PCB. But the thinner you get, then there is some kind of turnover that the price will rise again because the materials itself are getting more expensive due to processing issues, and especially here, an 0.1 millimeter core, that's basically a flexible core. So even if it's FR4, the thinner it gets, it tends to be flexible. So handling is more critical, even in our fab. So handling is a factor during PCB manufacturing, and therefore the price is going up again. And the same thing, the more material we use when it gets thicker, yeah, for sure, more material needs to be paid. So that's why the price is going up here as well. So it's some kind of curve where you have a minimum, and the minimum or optimum, as you see here, is somewhere around 1 millimeter, 0.8 millimeter, depending on the material, but that's somewhere where you need to show. So please ask yourself the question, if you have a 1.6 millimeter PCB, does it need to be that thick for my application? Or do I just do it because I did it in the past? And maybe I can change it going down to 1.2 millimeter, 1 millimeter, not too thin, like 0.5, 0.4, something like this. We could do this, but then the cost will go up again. So ask yourself what is needed, or did I do it so because I did it in the past? Another example here is a standard stackup versus an individual stackup. So on the left side, you see a standard stackup for a 6-layer multi-layer, how you would find it on our website and how we would do it if you just tell us you need a 6-layer multi-layer with 1.6 millimeter thickness. If you change it by your requirements, whatever that would be, but tell us, oh, I need to use 100 micron core in this stackup. For example, you need to realize a coil, for example, and the distance between those two coil layers, you have a double layer coil on layer 2 and layer 3 are here in this example, and the distance to have this inductance you want to reach, you only can allow to have a distance between these layers of 0.1 millimeter. That's okay, we can do this, but yeah, keep in mind to change this, and you already see this, we have additional cost because we have this handling of the thin laminate. It's not so stable in our manufacturing than the 0.36 millimeter. Plus, there are 4 more prepregs in the stackup. So this is again more handling during the actual stackup when we go to the multi-layer process, but it's just more material, more price to pay for these prepregs. So the price goes up. It's the same thickness. It's still a 6-layer multi-layer, but you have 16% difference in between the price due to this different handling and more prepregs in the stackup. So the question is, do you need this specific stackup? Then okay, but if not, then think about, would you tell us just use your standard stackup to go down in cost, and then we would use the one which is the easiest in production for us and the best from cost point of view, from a amount of prepreg and so on. The next example here, when it comes to individual stackups, and we see this, to be honest, quite often. Don't know where it comes from, but often the question is a core-based stackup. A core-based stackup means, on the right picture, you see this, that the cores are basically part of the outside of the PCB. So the top of the top core, the top copper of the top core is the outer layer copper here. So there is no prepreg in between the top copper and the inner layer core. The inner layer core basically is on the outside here as well. What's the problem here? Well, basically, when we do the structuring of this core, we normally structure top and bottom side in parallel when you go to the inner layer manufacturing, like you would see on the left side. For plating, we need to have a fully covering copper on the outer layers after the lamination. So this would mean that when we do the inner layer structuring here, in that case, layer 2, the top layer needs to be fully secured so that we do not etch away anything. We still need to photo structure it, but basically we cover everything with photoresist so that it's not being etched away. And when you sum this up, you will probably see that this core-based stackup needs to be treated with 2 additional photo structuring processes. So actually it needs to be treated like an 8-layer build-up, although you just get 6 layers. So this is additional cost because this top and this bottom layer is going through the photo structuring 2 times. Plus, there is just more prepreg, maybe some filling cores and so on involved to get to the distances. So this, these additional processes for the exposure and the photo structuring, again, this is here in that case, it's a 20 to 25% additional cost. You still have the 6-layer build-up. You even have the same distances in between the layers, just a different stack-up of prepregs and already hardened cores, and the different handling and processing here behind gives you an increase of price. So we would normally then, if we get this this stack-up suggestion from you, we normally get back to you and ask, can we change this to a foil lamination stack-up compared to core-based stack-up? So let's switch over to mechanical processing, and we will start here with the drilling. And an easy factor you all know is the more drills you have on your PCB, the higher the cost. That's just because it's a sequential process. What you probably do not know is that the thickness of the drill bit affects the price of PCB costs. Not only because the size means we have to drill slower, or the wear of the tool is less, but what we do in PCB manufacturing, we are doing what we call a panel stacking during manufacturing. So if the tolerances allow it, and if the tool is thick enough, we can stack panels on top of each other in the machine, and by one drill hit, we can make 2 holes or 3 holes in 2 or 3 different panels. And here you see this explained. The thinner the tool, the less on the one side. And if you look on this drill bit on the right side, you see this marker L2. So this is the length of the actual usable length of this drill bit. And the thinner the tool gets, well, the shorter L2 gets. So even if we could do it due to tolerance reasons or whatever, yeah, this length L2 is just for the smaller bits, just too short to drill 2 or 3 or more panels in parallel by stacking them on top of each other. Another thing would be the stability of the tool. The smaller the drill bit gets, the more it tends to be deflected when it goes through the material, so that the entry point on top is often not the same as the exit point on the bottom. And this might get to critical issues. For example, when you look on remaining ring requirements in IPC class 2 or IPC class 3, where you have different requirements, how big the remaining ring still needs to be so that it's an okay PCB. And another parameter you probably haven't heard of yet is the thicker the drill bit, the more strokes we can make with, so the more wires we can drill with it. And the thinner it is, the earlier we have to take it out of the drilling machine. And you see on the left side, we can make 1,250 strokes. On the right side, it's only 500 strokes. So let's sum up all these parameters. If you imagine you want to drill 15,000 wires, this would take us in manufacturing with an 0.5 millimeter drill bit only 0.2 hours. If you go down to 0.35 millimeter, it's already doubled because we do not have that much strokes and we only have a stack of 2. And if we have to only use 1 production panel and we only have 500 strokes, it would mean for the same amount of drills, we times 4 the time to drill all these 15,000 wires. The problem here with the usage of drill bits, if we have less strokes, then yeah, we have to use more drill bits and they cost as well. So if you compare it on the right side, we have 30 drill bits, which we have to use for these 15,000 wires, and we only use 4 drill bits for the 0.55 millimeters. So to sum it up as a cost factor, you see it's times 4.6 here in that case. To give you an imagination how thick are these tools or how they look like, we use a checkered paper here. Just place it on a checkered paper and you see how thin actually 0.25 millimeter bits are. And the question for you is, do I really need it to make them so small, or could I use wider, thicker drill bits? Again, it's probably in the most of the times it's a trade-off, because the thicker your drill bit is, the wider your pad needs to be, and maybe more size is needed on the PCB, and maybe your PCB is getting thicker. So this is contradicted to the fact which I told on the very first slides, that we want to make the PCB smaller. But yeah, again, it's like finding a trade-off, what would be best for this specific PCB. And again, another tip or another hint here, for the drilling, what is the cost factors? Well, we have a base cost, a fixed cost for the mechanical drilling, for example, the invest for the machine. And then we have the variable cost, depending on the drill bit, and the thinner the drill bit, the higher this variable cost will be according to the number of wires. But let's compare this, for example, to laser drilling. And we will come to this fact a little bit more in detail later on in the webinar, because the question is, could you get down in price by using laser drills? And first of all, yeah, the invest in such a laser equipment is more. So a machine costs us more than a standard mechanical drilling, but the variable costs are getting less the more wires you have. So there is sometimes there's a turning point in cost where it could be more beneficial if you switch to laser drilling, because laser drilling on the one hand is just much faster. So you have less processing time and you do not have the drill bits in cost. So the more drill bits you need, you do not have this for the laser. For sure, we have in some few years, you need to change the laser source, yes, but this is a one time in 5, 6, or 7 years, depending on how long this one source will last. But we do not have drill bits here. So the cost of the drill bits and the much faster drilling leads to the fact that the variable costs for laser drilling are less. So there is some point where it's cheaper to use laser drilling compared to mechanical drilling. So when we do the laser drilling, when we go to microwires, the next question always is, do I need to fill the microwires or not? Why does this question occur? Well, basically you see it here. If you have unfilled microwires, it could happen that you have voids in your solder joints. Here in this case, it's a ball of an BGA. The question is, what is tolerable? And when you look into IPC 1795C, class 3 would mean 22% of the image diameter, when you, for example, take an X-ray picture, is still allowed to have voids. So would this be okay for your application or not? And this void formation depends on a lot of things. On the one hand, it's the size of the micro VI itself, so how much air could be inside, but on the other hand, it could be part of the flux or the solder paste you use, the temperature profile of your solder process, and the uniform heating of the printed circuit board during the soldering. So there are some facts which we, as a PCB manufacturer, cannot have a direct influence on, which is more part of your manufacturing. What we can do is to get rid of it, we can fill it. Yeah, that's true. But this comes with cost. And depending on your stack up, for example, if you already have resin filled through holes, then you could think of not doing a copper filling like on the left side here of the microwire, but instead use a resin filled microwire with overbladed copper, so that you still have a almost smooth surface with no dimple, and still have the fact that there is almost no void creation. So that's something you have to think of, but it comes with cost. And why is it more costly to fill these microwires? Well, this is explained here in this slide. It's a little bit a different process filling a standard microwire compared to so only fill the sidewalls, I have to say, then completely fill the wire with copper. For a copper filling processes, you need to have different baths with different ingredients. And here you see what's basically being used. The most parts is you have like a wetter, a leveler, and a brightener. The wetter is basically being used. It's molecules which occupy the surface of the PCB, and therefore where they are, they block the deposition of copper. Then you have the levelers. Those are molecules which accumulate at the location with the highest current density. This is basically on the edge when you go from the top surface down into the hole. And then you have the brightener, which is to reduce the copper crystal sizes so that it shines more. And the better and the smaller the copper crystals, the more uniform the plating is. So what happens with these three molecules, basically you build up the copper in this hole from the bottom up to the top, and you hardly have any copper deposition on the top surface of the PCB due to the wetters. But this takes time, and compared to just having the sidewalls being plated, This takes 2 to 3 times longer to just fill up this PCB. So the panels are just longer in the plating baths, and the longer it takes, the more it costs, basically. And to show you how this looks in real life, you see this sequence here, the time sequence. So it builds up on the sidewall as well a little bit, and then from the top on it fills up the microwire, so that after 1 hour, 20 minutes, the wire is being fully copper plated and filled with copper, compared to 20-25 minutes if you only plate the sidewalls for a standard microwire. So ask yourself the question, as I said, do I need copper-filled microwires, or can I live, for example, with some voids in my BGA balls? And we have quite a lot of applications, even in the automotive area, truck gearboxes, for example, which run since 20 years out there on the market without any defect, where we didn't copper fill the microwires. We have small, or the customer has small voids in his balls, but it's all tolerable and still pretty reliable in that case. Another influence for the cost is the construction of the PCB itself. When you look on the HDI layer construction, so how many pressings, for example, do I need? Do I have a single lamination? Do I need to go 2 times into the press, or even 3 times? So I won't go too much into the details of this chart, but it just shows you the complexer the build-up will get, the more microwires you need, the more buried wires you need, the more pressings you need. Well, the higher the cost factor would be. Could be even more than 175% on the top side. If you have 2 pressings, 3 press, sequential laminations, whatever, it could almost double the price of the PCB. So take in mind, and basically what I want to say with this, come to us, talk to us, so that we find the best and optimal solution for you, for your stack up, for your components which need to have a fan out, and so on, to see what would be the best option in a layer construction here for you. And the last part of the mechanical processing basically is the final routing. And routing, again, is just like the drilling. We have the same option here. We can do the panel stacking. And again, due to different drill bit diameters, we can either stack more panel or less panel. Plus, the tool life is different. So the wider, the thicker the tool gets, the more distance we can route with the tool. And here we have some figures. I won't go too much into the detail, but when you look at this, the less distance you can route with it and the less panel stacking you can do, you see you just need more routing bits to do the same distance in routing. For example, here I used as a basic 100 PCBs with 0.5 millimeter routing path for 1 PCB. So it's a little bit more than 1 routing tool for 2 millimeter routers. And it's almost 17 tools during this process needed when we just go down to 1 millimeter. So you see, this is the reason why we have like a standard of 2 millimeter or 2.4 millimeter, depending on the technology, as a standard tool, which we normally would like to use due to the tool life and the possible panel stacking. Another thing, another parameter is the feed. So how fast can you route? And the smaller the tool gets, the slower you need to get to the FO4 material. So this again sums up to route time. And again, this example, 100 PCBs with 0.5 millimeter routing path from only 0.2 hours to 2.8 hours. It's still the same distance. It's just a smaller tool. And it means the time increases. How long does the panel lie on our manufacturing equipment, the more it costs. So here in that case, when we sum up everything, all the parameters, it's times 12 compared 2 millimeter to 1 millimeter routing tool. Pretty interesting, I think. We know that often, it could happen that complex routing contours are needed due to whatever reason, maybe due to your housing or whatever. But just keep in mind, a square rectangular is always cheaper than having a lot of complex routing contours. And especially if the distance in between those contours is less, we need to go down with the drill diameter, with the routing diameter. So the cost can get very high compared to a standard rectangular built-up. So just keep that in mind for you. Let's move on to the enhanced technologies. So what are further cost drivers? I already told you PCB thickness, layer count. It's not only relevant for the drilling routing, it's just the material, the excessive material being used and so on. The number of laminations for sure, it's just much more processing to go 2 times to the pressing department, but 2 times going pressing department has a lot of other different standard processes, cleaning and so on involved. So the more processes, the more costly it gets. Another thing would be edge plating, side plating. If you maybe do not know what it means, this is what it looks like. So you can have copper on the outer edges of your PCB as well. You can have it, not everywhere, but you can have it in specific areas. But this means that we have to split the routing process. So the final routing needs to be split, while the part where we have the edge plating or the side plating needs to be done in the same process step as the drilling of the vias is being done, so that afterwards we can plate copper there. So we need to go 2 times to the routing machines and using a process. Basically is the same. Oh, sorry, I was just told that we have problems with the sound. So I needed to switch the microphone now. I hope you can hear me again. Okay, so I will just repeat this foil. So the PCB thickness and the layer count on the one part is definitely a factor which you need to take into account, as well as the number of laminations being used. So if you go to the pressing department 1 time or 2 times or 3 times, there are quite a lot of processes before and afterwards needed. So you have to pay all these processes 1 time, 2 time, or 3 time, and therefore the cost goes up. Then you have the edge plating, the side plating as an additional cost. And you see it here on the picture on the top right. If you need this, it basically means for us that we have to split our outer layer processing. Parts of it need to be done already in the stage when we do the drilling of the wires, so that we can do the plating of this of these edges. So yeah, basically you can imagine if we have to go 2 times to the routing department with these panels, it's 2 times the cost almost, because we have the same setup for the second process. We have a little bit less routing time, yes, but still it's 2 times going to the department where the routing takes place, and therefore the cost is higher. We have the same basically for castellated holes or castellation, depending on how you would call it in your area. And you see on the bottom picture what is meant by that. So you have those half opened vias directly sitting on the edge for electrical contact. So when you want to do a soldering, for example, here in that case. But again, this means to split different mechanical processes from the end routing towards drilling of the vias in front. So again, we have to use several processes several times, and this means the cost goes up. Please take in mind, look into our design rules, because the smaller, for example, for the castellated holes, the smaller those holes get, the more critical they are to be opened during this processing, so that you have a half open wire. And there is a limit which cannot be overcome in the size of those wires. The smaller they get, there is sometimes a point where we cannot realize it. So please have a look on the design rules of castellated holes. If you won't find them on our website, just contact your salesperson or just contact me or every person you have from Würth Elektronik, and we can send them to you and tell them what basically is needed for those castellated holes. So what else do we have? We have the colored solder resists, white, black, red, blue. Well, basically there is almost every color out there on the market. For us here at Würth Elektronik, green is our standard. Why that? Well, basically, our biggest problem is the demand of all the other solar servers is just extremely low. What does it mean? If the demand is low, we cannot afford to have a second line. For example, we have a line for green and we have a line for black or a line for red. That just doesn't make sense if you have to use it only 2 hours per week. and the remaining part is just debt investment, you can say. So what would we need to do if we want to have another colored solar resist? Well, we have to clean our machine, have to use the different solar resist afterwards, clean it again to go back to green. Again, this is high cost, and it's still a reason for quality that can happen just quite a lot. So that we decided green is our standard, and we basically are not using other colored solar resist. But the question again here is it needed? So does it always have to be another solar resist? We know that a lot of you would, for example, like to have a red solar resist to mark your PCBs as prototypes or samples without a series approval, so that everyone in your fab knows those are pieces which are not allowed to leave the fab and to go to your customers. But couldn't it be an option to use, for example, legend printing for this, so that you print in specific areas on almost the whole PCB a legend print in the color what you would need: white, red, black, and underneath you still have the green solar resist so that the soldering still can be done, but you have in the legend printing process the color what you need. This would be a real good option to combine the functionalities here. So just think about it, if this would be a possibility for you. Instead of using a red solar resist, maybe use a red legend print on top of a green solar resist. I did already mention the legend printing. Another thing here is how small does it need to be printed? There are limits here as well. Maybe even your system cannot read it afterwards, but we need to have a resolution so that we can print it. But ask yourself, how small does it need to be? Or do you even need it? Sometimes we see for customers that maybe they forgot, because during prototyping, when they did a hand assembly, they had the legend printing to see where all the components need to go. But when it goes to series manufacturing, it actually isn't needed anymore. So then just tell us, get rid of it, and that's it. Another thing is, in the CAD systems, there is often the problem that legend printing overlaps the solder pads. So this is a point for us, what we always need to check during input and design ruling, to see to do the design rule check. Is there legend printing going on top of the solder pad? So then we have to remove it during our CAM phase. And again, it's a quality thing. Maybe the software is not quite intelligent, and there is some place where we have forgotten to remove it. So there is always a danger of printing, of legend printing on top of pads. And this is just a risk. We maybe find it during our quality inspection, then the yield goes down. Again, cost factor. So ask yourself, do I still need the legend printing or not? How big must it be? Where does it need to be? And so on. So just check it to make sure you get the optimum out of it. Another factor is required or needed impedances. And here we have two different options. One is the so-called impedance watching, or the controlled dielectric. And here we, together with you, calculate basically a stack up and the width of the tracks. And based on this, you create your layout. And we build the PCBs based on what we agreed on during this calculation. There are no coupons involved, because we know basically how our processes behave, how our distances behave, how our pressing behave, so that when we say use this stack up with this track width, it's in most of the cases okay, so that you get the impedance out what you want to have for your application in the right tolerances. Still, we could introduce coupons, and this is then called impedance controlled PCB manufacturing. This means that at the end of the manufacturing, we take this coupon, we measure it, and we directly show you that we can and that we fit the desired impedance to the tolerance which is needed. But please take in mind that if we need those coupons, well, they need space on the manufacturing panel as well. So then it could happen that we cannot fit as much PCBs on a manufacturing panel as if we could without those coupons. So it's always mostly in, I would say 95% the case that we have a reduced number of PCBs on a manufacturing panel. And additionally, you have the cost for the testing. This is not an automated process. In most of the fabs I know, I hardly know any fab which has an automated process of the testing of these coupons. So it's always a person taking the coupon, going to the measurement equipment, taking the measurement head, placing it under the coupon, start the measurement, protocol it, print out a document, and so on. So it's quite a long process to do this, and this is cost which you need to pay. The question is, do you need it, or do you rely on our quality and on our knowledge that we just calculate it and build it based upon our knowledge and based upon what we agree on? Okay, next technology would be filled and capped vias. So what is it? Well, basically you see it here. We take a through hole, we fill it with resin, and we overplate it with copper. Where do you need it? Often it's being used in cooling areas. For example, you want to get rid of solder going into through holes. So you overplate them that the solder still stays on the surface, but you still have the via in the solder pad so that the heat can go from front to backside, for example. Well, the question is it necessary, or maybe could it be avoided with intelligent design? You see this here in this picture on the bottom right. In the left footprint, you have those cooling vias in this solder pad in the middle. These definitely need to be filled with resin and overplated with copper so that the solder doesn't go into the hole and goes to the backside. But do you need that amount of vias, or maybe you could work with less vias and maybe you can make just a rectangular array so that the heat still goes from the front to the backside? But you're using standard technology. You do not use filled and capped plated holes. You just use standard technology, standard through holes. It would be much cheaper, and maybe it's still the same result when it comes to heat management. So come to us, talk to the colleagues from our heat management team. They will advise you and give you hints and tricks if this could be done or not. So next part, your request would be, please manufacture the PCBs according to IPC class 3. So you normally have a reason to ask us to produce boards based on IPC class 3. But we sometimes see, and not sometimes, we quite very often see that maybe this request comes from just a different technology you would like to use, and you say, oh, I need to have 25 micron copper in the barrel. For example, a press fit assembly could be such a reason why you want to have 25 micron copper in the barrel instead of 20 microns. And yeah, you maybe have seen that 25 micron copper is part of the requirement from IPC class 3. So yeah, that's fine. I just write down IPC class 3 production. So then I can get 25 micron copper in the barrel. That would work, but please take in mind IPC class 3 is not only 25 micron copper in the barrel, it has much more requirements behind. 25 microns copper barrel is just one part of this requirement. And this additional requirements mean we have just higher cost, because one big part here is the tougher test criteria in accordance to IPC class 3, which basically lower our yield because we just have to check much more. And sometimes IPC class 2 would be okay, IPC class 3 wouldn't be okay. There is mostly less space on the production planet because we need to use more coupons to test all these criteria to see, do we have the correct copper thicknesses? Because even on an inner layer, we need to have a higher copper thickness compared in class 3 to class 2. So we need to have thicker copper. We need to check this. We need to make sure that there is enough copper here. So not only in the barrel, but the height of the copper tracks on the inner layers needs to be more as well. So there is just a higher inspection effort where we need to check those coupons under the microscope and document it so that all these, we call it the inner values, are being documented so that IPC class 3 can be assigned to the printed circuit board. On all these together, well, this is just a higher price. And if you just need 25 microns in the barrel and can neglect all the other criteria of IPC class 3, then please do not write down IPC class 3, just write down 25 micron copper is needed in a barrel. And this is just one requirement which we agree on. On all the other, PCB is still being manufactured according to IPC class 2. So this is a part where you really can save again a lot of money. Just give us the right specification of your board. Please take in mind what is needed and use this and not over specify your board based on your need. So let's move on. Different technology. Now we will go to rigid flex. And here a comparison between rigid flex or flex rigid, depending on your area, you call it one or the other way. Here you see on the left side a 1F5RI, which means you have 6 layers and you have a polyimide area with 1 copper layer going on top of it. And on the right side, you have a 2RI, 2F2RI, which means you have in the middle of the board a polyimide layer with a copper layer on top and on bottom. So it's still both a 6-layer board. It's both an HDI 1-for-1, so you have on both boards 1 microvia layer involved. But you see already the difference when you look on the effort for the mechanical depth milling to realize the flex area. On the left side, you have just 1 mechanical depth milling. On the right side, you have 2 mechanical depth millings. This means on the right side, you do the milling from the front side, then you have to turn around the panel, do the milling from the back side. It's 2 different milling processes, so the cost goes up due to the effort of turning it around and going to the milling a second time. Then there is a difference in the cost for the flex material. Again, copper is involved, and here in this part, we really buy it. We buy polyimide with 1 copper clad layer, and we buy polyimide with 2 copper clad layers. And we have already learned in the earlier slides, more copper means more cost. So the left side is cheaper than the right side from a material point of view when you look on the polyimide layer. On the left side, we can use a screen printing process for the flexible solder resist. We just recently changed this even to an inkjet process so that you even can get rid of the screens themselves. We just use the inkjet. On the right side, this is not yet possible. We are working on this, but it's not yet possible. So here we still need to use a pre-routed and laminated cover lay on top and on bottom of the structures, of the copper structures in the flexible area. And the cover lay is just much more expensive than the printed flexible solder resist. So again, it's a price factor here inside. We are working on the topic that we can use inkjet printed flexible solder resist on the inner layers as well, but we are not quite there yet, so it's still in work. But the outer layers, they can be printed already with the inkjet, so cheaper than already pre-routed cover lay. One thing, take in mind, you have a higher reliability when it comes to cover lay. When it comes to cracks in the material for dynamic reasons, then it might be advisable to still use cover lay. And then in that case, it would be partial applied cover lay, so that in the other areas where you have drills, there would be no cover lay, only where it's needed. But to sum it up, the left side, this build-up is much cheaper than the build-up on the right side. So ask yourself the question, how many layers do I need in a transition between those 2 rigid parts and the flexible area? Is 1 layer enough? Or do I need 2 copper layers here? Sometimes it's needed. For example, if you have impedances here, if you have a strip line with a ground layer, then for sure you need those 2 layers. But sometimes it's not needed, and therefore, why using it? If you do not need it, then you can go to the left side where you only have 1 copper layer in the flexible area, and you can save money. Okay, so now let's come to the last part of the webinar. It's the tips and tricks. And here I have one example when it comes to total cost of ownership. Or if you look on a system here, I have an example with me of a system of 4 PCBs. If you take 4 rigid PCBs, you have 4 different layouts. Those 4 different layouts need to be done. They need to be manufactured. And if you want to connect those 4 different PCBs, it's often being done by some flexible connectors. And well, basically, if you connect everyone, the handling would be that you have to handle at least 7 different parts, depending on the build-up, what you want to do. You at least have 4 different soldering processes, 4 different setups for the soldering process, and so on. And you need to do at least 4 test runs. We need, in our electrical test, do 4 different test runs, but you for yourself as well. Maybe even a 5th for the final setup, for the final assembly. So that's why I wrote minimum 4 test runs. And you have the logistics behind in your storage. You have 7 different parts which you need to find, which you need to set up, and so on, and which you need to store. Sometimes it's better for your total cost of ownership if you look on rigid flex PCBs. You could combine everything in one layout. This one layout, those 4 rigid areas are already connected with the flex here in that case. For you, it would mean you only have to handle one part. You have a minimum of 1 soldering process. I always say minimum. If you have a front and backside assembly, it would be 2. If you have front, backside, plus through-hole components with wave soldering, it would be 3, whatever. But it's if you only do 1 set of soldering processes compared to 4 sets of soldering processes on the left side. You have 1 test run, so we test in our fab all 4 rigid parts together with the flex part, and you can do 1 test when you did the assembly of the boards instead of several different tests when you do the separated setups, the separated soldering, and so on. And you just have the logistic for 1 part. You do not have the logistics for 7 parts in your warehouse and in your setup. So what is your profit? Well, you have 1 layout routing logistic. You do everything in one. The team, the layouter, and the developer has to think of only 1 setup and not 4 different setups. You have no uneven quantities of parts in your storage. So maybe PCB1, you have 10 pieces. PCB4, you have 80 pieces, and you want to assemble 20. Oh, we're missing 10 of PCB1. Then you have to order them due to whatever reasons. It takes time, and maybe it has too long lead time. You cannot work with it. So you have to just you have the possibility and the benefit to just look for after 1 part instead of 7 parts. Then you have less setup time during your assembly because it's 1 assembly process and not 4 different processes. And you have less time spent during testing. And your logistics and handling, well, they are just simplified in complexity. So it's just less effort here needed. And therefore, we've seen quite a lot of examples in the past where the total cost, even if the rigid flex PCB is more costly compared to the price for the 4 PCBs, but the total cost of ownership, the overall system, your cost, often comes down by combining the technologies intelligently. And here in that case, it would mean maybe it could be a benefit using rigid flex instead of 4 PCBs connected with 3 connectors. Another hint and tip, I call it reduce prejudices. So often we get to hear from buyers, HDI PCs, they are just expensive. They're much more expensive than standard PCBs. I do not want to do this. And I told my developers and my layouters not to use this technology because it's expensive. But is that correct? Is that right? Well, let's do a fact check. And to show you that this doesn't need to be the case, I was just looking here in that case onto the fan out of a BGA with a pitch of 0.8 millimeters. It's 400 pins, 10 rows. And if you want to do the fan out with plated through holes, well, let's see how many layers do you need to do the fan out. So you have the through holes, then you go to layer 2, you have your remaining rings, your pads and the holes. And due to the size, well, here in that case, you just can fit 1 track through the pair of pads to go to the outside to do the fan out. Then you need to go to the next layer to get the next set of tracks down to layer 4, 5, 6, and even go down to layer 7 to do this fan out for this BGA. So it's 7 signal layers needed for that because you still, even on layer 7, well, it's through holes. The holes are there, and where there is a hole, you cannot make a track. That's basically it. Now let's compare it to HDI microwire setup. So the pads needed here are already smaller. You can even do very easily, as we've seen, a microwire in the pad itself. You do not need to do a dog bone structure or whatever. And when you go down to layer 2, due to the fact that those pads are much smaller, in between a set of 2 pads, you could fit 2 tracks already. So it means already on layer 2, you can do the fan out with more tracks here. And since you do not have a through hole, since there is no hole here on layer 3 where you do not need it, you have much more space to do the remaining fan out. And here in that case, with the usage of layer 3, so it's just 2 copper layers going from top to layer 1, and going from layer 2 to layer 3, you could do the fan out here, and it's not more layers needed. So what it means is you could come to the fact that you reduce the amount of layers in your PCB built up by the usage of HDI microwire compared to plated through holes, and the less layers needed, the thinner the board is. You've already seen it costs less. So still the fact of using microwires, the reducing of signal layers could be that the cost could be reduced. Another fact here, by using microwire, we are talking about miniaturization. So the pads for microwires are smaller than the pads for the plated through holes. And by using this technology, we've seen quite a lot that those PCBs, they can be reduced in size by 10 to 20%, depending on the components, depending on different stuff, but you can have a reduction of size. And again, we've seen in the beginning of the webinar, a reduction of size of the PCB means a reduction of cost. So now you already have 2 parameters. You can have less layers and less PCB size. So you really can come to the point that the cost goes down by using HDI microwire technology due to those 2 parameters. So we have a team of experts here. Contact us, for example, Andreas Terea, Mr. Künkel. They can advise you. They can sit together with you, see if for your application it could be advisable to go to HDI technology to even save cost by using, on the first hand, you think it's a more expensive technology, but in the end, it could be cheaper by changing the technology here. Then some more soft factors, what we can say, for example, the connection of pads, some CAD tools. When you look on the top left part, some CAD tools do not find this critical part here, this very low distance in between the track and the pad, because it's still the same net. So often the design rules do not find this point here, but this is getting critical for us during manufacturing. Why is it critical? Well, we can have pseudo errors during design rule check or during AY, so that we scrap quite a lot of PCBs due to that fact. So the yield is going down, and we need to calculate this. So if the yield is going down, we need to set up more PCBs. We have an overload of PCBs. We need to manufacture more, so the cost goes up. So please try to avoid, for example, this pad connections or just too close to the pad, or even not only pad connections, the same net distance again needs to be checked as well, so that this doesn't happen here in that case. Another thing what happens quite often, to be honest, is the clearance from, for example, here in that case, copper to the outline. This is an example from an inner layer where you see this inner layer pad. The distance here from the inner layer pad to the copper edge in the layout was 152 microns. In our design rules, we have 250 microns. So this is not according to the design rules. We could do this, we could realize this, but this means we need to have different handling processes. We need to slower down the routing. We need to have thinner and smaller tolerances and so on. So this means please follow the design rules. The design rules give you a hint where are we feeling quite comfortable, I would say, so that everything from a quality point of view and from the running, how we are running our machines, is everything okay. If you go beyond the design rules, it often means we have to slow down processes, and it might be okay when you talk to us that the board still works, but sometimes it can come to the point that the board is non-manufacturable, so that we have to decline this so that we cannot manufacture it. So please try to follow the design rules. If not, talk to us, but then please take in mind it will lead to higher cost if you need it for your application. Well, then we have some special requests. Here is an example for a special request in packaging, and it's quite an extreme example, but it's a real life example. So during manufacturing, we had to basically build a double-sided PCB. Here, this semicircular PCB. The order was 2,600 PCBs. So we had to manufacture 14 production panels. And this is quite a typical lot for our manufacturing. Could be more, could be less, but 14 production panels is quite typical in our manufacturing. Now comes the interesting part. Our customer asked us to please stack 4 PCBs on top of each other and use a specific adhesive tape to fix those 4 PCBs on top of each other. So this is a hand process. It's a specific adhesive stripe, a specific adhesive. So this takes already quite some time. But then comes the second packaging unit here. And here the customer asked us, please use this base carton. So the size of this base carton was really exactly specified due to his handling. And please place all those packages from the first unit in that format onto the second packaging unit. So quite some demands here. We did it, but please take in mind the packaging of these 2,600 PCBs took us 10 hours in effort to only do the packaging. So this is quite a cost factor which we need to be honest, need to calculate as well and hand it over to you. So if you need it, okay, but please take in mind it costs, and if it's not needed, try to avoid it. Yeah, so those were the points I wanted to show you today. And in the summary, well, basically you get all those points. I won't go into detail of this foil. You will have it in the documentation afterwards in the webinar. So I would like to say thank you for joining.